All right, welcome to the Statistics Review Part 7. In this video, I'm going to talk a little bit about point estimation and then also interval estimation for the population mean. So point estimation, we use the data from the sample to compute a single value, so that is 1 point, of a sample statistic that serves as an estimate of a population parameter. So we have, for example, a population parameter mu, parameter for the mean, and x bar is a point estimator. It's going to be one number, 1 point, it's a single value that gives us an idea about what mu might be. Now, something to note with a point estimator, such as x bar, is that it's rarely going to be the exact value of the population parameter. Right? It will probably be wrong. The probability that x bar will equal mu is 0. Right? If we have a continuous distribution, the probability that we've happened to get the exact right value, that our sample led us directly to mu, is 0. So an interval estimate can be computed by adding and subtracting what we call a margin of error to this point estimate. So we would take x bar and add and subtract a value to it, giving us an interval. So the general form of an interval estimate of population mean is x bar, that's our point estimate, plus or minus the margin of error. So we go from having a continuous distribution where the probability that x bar equals mu is 0 to having an interval. If you see here what I've got written out, we take our x bar and then we have some interval around that, right? Mu minus the margin of error, mu plus the margin of error. This probability is positive. There is some positive probability that x bar will be between mu minus something and mu plus something. Right, so in this case now we have a positive probability that our value, what we found, x bar, is within some range, as it were, of mu, or some interval around mu. So that's part of the idea there with getting an interval estimate, is that we get a positive probability that our value is within that range, that interval. Some concepts here, some vocabulary in thinking about this idea of an interval estimate is that we need a confidence coefficient. So this is the probability that the interval, that x bar plus or minus the margin of error, contains the true parameter. So note here that this parameter is not a random variable, so that value mu is not the random variable, but the upper and lower limits of the interval, so the x bar plus the margin of error and x bar minus the margin of error, those are random variables. Now we have a confidence level, and that's just the confidence coefficient expressed as a percentage. So for example, if the confidence coefficient is 0.9, that's a probability, then the confidence level would be 90%. And the percentage of confidence intervals constructed in this fashion that would contain the true parameter. So if the confidence coefficient is 0.9 and the confidence level then is 90%, what that means is that if we went through this process a large number of times, 90% of those intervals would contain the true parameter mu. And then another term we use sometimes is that of significance level. So here we have this Greek letter alpha, and that equals 1 minus the confidence coefficient. And sometimes people express it as a percentage. So in this case, let's say the confidence coefficient is 0.9 again, then 1 minus 0.9 is 0.1. So if we had a confidence coefficient of 0.9, alpha would be 0.1. So here, there are two primary cases to consider when constructing confidence intervals for mu. And those cases are, one, that we know what the population standard deviation, so sigma, and that is known. We assume that we know it. So in this case, we construct the interval using a z value. The other case here is the researcher does not assume that she knows what sigma is. Right? Instead, we use the sample standard deviation, so S, to make this calculation. And here the interval is constructed using a t-value, what is called a t-value. So the difference here primarily is that we're either going to use a z or a t-value in constructing the interval. So to go over these each, let's suppose that sigma is known. In constructing confidence intervals for mu, when the value of the population standard deviation sigma is assumed to be known, you can use a z-value to determine the margin of error. And here I've got the formula for the margin of error written out. It involves a z-value, it involves sigma, which in this case is assumed to be known, and the sample size, the square root of the sample size. This term here may look familiar. It's what was called the standard error. So that may look familiar to you. So that z-value is the z-value with an area or probability of half of alpha. Again, that alpha was the significance level so that half of alpha to the right. So example, if the confidence coefficient is 0.95, so you're constructing a 95% confidence interval, then alpha, that significance level, is 1 minus 0.95 or 0.05, and alpha over 2 is 0.025. And so then the z-value for that is 1.96. And here's a graph illustrating that yellow shaded area to the right is an area of 0.025, and that begins at z of 1.96. The most common confidence intervals to construct are 90%, 95%, and 99% confidence intervals, and the corresponding z-values are illustrated here. So an example, we have a random sample of 50 observations from a population with standard deviation of sigma equals 6, so 6 is the standard deviation, and it had a sample mean of 32. So if we want a 90% confidence interval for the population mean, what we're going to do here is we're going to take the starting point is x bar, right? So this part here is x bar, and then this value here is our z value. Then we have sigma goes in there, that part of standard error, and then the number of observations n fits in down here into the denominator, so we take the square root of n. If you make this calculation here, 6 divided by square root of 50 times 1.645, you should get 1.3958. And then to get the confidence interval, we simply subtract that to get 30.6 and add that to get 33.396. And that gives the confidence interval. So another example, slightly different here, but to hopefully firm up the concept. We've got a simple random sample of 60 observations from a population with a standard deviation of 5 and a sample mean of 14. We want a 95% confidence interval. So what's changing here? Changed all the values, but again, 14, the sample mean, goes right here. Right, this is your x bar. Since it's a 95% confidence interval, we get 1.96 as our z value. Right, this is z here. And then again, the other pieces just come straight in from the problem. Sigma is 5, and n is 60. Goes in there. You can pause the video, take a minute to crank through this, verify that you're getting the same values, same numbers, but then you get a 95% confidence interval of 12.73 to 15.26. And that would be your 95% confidence interval in this example. The other case that we had is when sigma is unknown. So when the standard deviation is not known, you construct the margin of error using a t-value instead of a z-value. So we're going to use a t-value in this kind of scenario. Now, something to note here is that the true population parameter sigma that we were using in the previous couple of examples, is never truly known. But when it is obtained from, you've got a larger sample from past data, you've got previous studies, in some of these situations, statisticians will assume that it's known and treat the value from previous studies or data as the known value for sigma. So just a little side note there on why statisticians, or the scenarios where statisticians might actually assume that sigma is known. But here we'll consider examples where we're going to use a t value. So we're going to look at the t distribution and see what that is here. So if x bar and s, so s is the sample standard deviation, are the results of a random sample, and x bar is normally distributed, either because the x values are normally distributed or because the sample is large. So go back to the central limit theorem and its implications. So let's think about the sample size being at least 30. Then we get something here that might look familiar of a sort. Here, x bar minus mu over this standard error here. This follows a t distribution with n minus 1 degrees of freedom. So what is this t here? Well, so this t is what you see defined here. It may look similar to what before you had as a z, right? Z before you maybe had x bar minus mu over sigma over square root of n. This would be z for the sample mean, right? So what's been changed in here? Well, all that's happened here is we've gone from having sigma to s and from z to t. And those are the things that change in that scenario. So what about the t distribution? The t distribution is a family of similar probability distributions. A specific t distribution depends on a parameter known as the degrees of freedom. So that's n minus 1 in these cases. The degrees of freedom refer to the number of independent pieces of information that go into the computation of S, the sample standard deviation. A t distribution with more degrees of freedom has less dispersion, and as the degrees of freedom increase, the difference between the t distribution and the standard normal probability distribution becomes smaller and smaller. So conceptually, as n gets very large, the difference between t and z becomes less and less meaningful. So here's an illustration of that. The black line that you see at the top, right? So the very far line, this is z, and these other two are t distributions. So this blue has degrees of freedom, or this, so the blue line has degrees of freedom equal to 5, right? And this dotted orange line has degrees of freedom equal to 25. So just as an example, as n increases and the degrees of freedom increase, you get closer and closer to the black line for the z, or standard normal distribution. It just gives you a quick example of what the t distribution looks like. So in this case then, what will change is that instead of using sigma, we have s here. Instead of using z, we have t. Those are the changes in this setup. So again, 1 minus alpha is the confidence coefficient, and this t value here, t with alpha over 2, half of alpha, it's the t value providing an area of alpha over 2, so half of alpha, in the upper tail of a t distribution with n minus 1 degrees of freedom. Right? So that's what we're looking at there. It looks very similar. It's just instead of a z, we use a t right here, and instead of a sigma, we've got s right there. So otherwise, the interval looks quite similar. Right? We're starting with the point estimate X bar and adding and subtracting a margin of error. So a little example here is credit card debt for the population of U.S. households. Say credit card balances of a sample of 70 households provided a mean credit card debt of $9,312 with a sample standard deviation of 4,007. So here, identifying these little pieces, this 70 is N, the 9,312 is X bar, the 4,007 is our S. This here also means we're going to have 69 degrees of freedom, right? That would be N minus 1. We're going to create a 95% confidence interval estimate of the mean credit card debt for the population of U.S. households. We're just going to assume in this example that the population is normally distributed. Okay. So we have a 95% confidence interval. That means a significance level of 0.05. So alpha over 2 is 0.025. We get 69 degrees of freedom. That's N minus 1. And now in this case, you can look on a t-table to find a t-value of 1.9949. You can look in other places. You might have a calculator that gives this to you, Excel or some other computer program. There are different ways that you might be able to look up what the t-value is. So just, different scenarios. On a particular exam, so a CFA exam, you wouldn't have access to Excel. So I don't know what resources might be available in terms of finding a t-value if you're asked to compute this, but in this example, the t is 1.9949. So just plugging that into the formula that you have for the t, for using the t value in constructing a confidence interval, you're using this right here. So again, the 9,312, that's the X bar. The 1.9949, that is the t value that you would get. The 4,007, that is your S. The 70 is N. And that's just a matter of plugging those things through. Pause the video and double check that the margin of error is 955.4. These values would be in dollars. But when you add and subtract that, we're going to round to the nearest dollar, and we get a 95% confidence interval. So we're 95% confidence that the mean credit card debt for the U.S. population, the population of U.S. households, is between 8,357 and 10,267 based on this example in calculating the confidence interval.